All right, so we're going to do one more quick example in this video. That's going to be oxygen, triatomic oxygen. This is called ozone. Just so you know, this is ozone. And it's different from O2 diatomic oxygen, which we usually talk about. You've heard of the ozone layer. This is a different allotrope of oxygen. But anyway, so we want to know the Lewis structure of this, the shape of this, the molecular shape, and the steric number, and the bond angle. Okay, so O3, each oxygen has 6 valence electrons. That's going to get us 18 valence electrons. And so, well, all oxygens are the same at this stage, so we're just going to put them in a line and connect them. And now we have to use our 18 valence electrons. So we've used 2, 4. We've used 4 of them. We have 14. So 6, 8, 10, 12, 14, 16, 18. That's how that would work. But now we have to check to see if we're satisfying the octet rule. We are on the central atom, 2, 4, 6, 8. We are on this atom, 2, 4, 6, 8. We are not on this oxygen, 2, 4, 6. That tells us we're going to have to bring one of these lone pairs down into a double bond. And so let's erase that and make a double bond there. Okay, now at this stage, we look to be good. We have 2, 4, 6, 8, and we have 2, 4, 6, 8, and we have still 2, 4, 6, 8. And again, we have 18 valence electrons. Hopefully, you can see pretty easily that there's a resonance structure here where the double bond is simply on the other side. And your molecule would look like this. So these are completely equivalent resonance structures. If you did the formal charge analysis on these, you would get the same thing. Basically, you just flip this whole molecule on its head. So it's telling you, in actuality, you don't have a double bond here. You don't have a single bond here. You have a 1.5 bond here and a 1.5 bond there. Okay. But anyway, that's not what we're focusing on this question. We're focusing on the shape, right, and the molecular geometry. So what's the steric number? I forgot a lone pair there. Sorry. The steric number here is going to be what? In both cases, both resonance structures, it's going to be the same. It's going to be, well, we have 1 lone pair and we have 2 bonding sites. So that means steric number equals 3. Okay. That means our steric geometry is going to be the geometry that gives 3 points in 3-dimensional space as far apart as they can be from one another. That's a triangle, basically a planar triangle. So it's just a normal triangle. Trigonal planar, we call it. Now the molecular shape is the next question. And that's going to be bent. And remember, the way to visualize that is you took a triangle, right? A triangle shape. There's a triangle. But you took that triangle and you just lopped off one of those sites where there's a lone pair. And what are you left with? You're left with a bent shape, right? That's bent. So you're left with something that just looks like that. And so, really how I drew this here isn't best. I drew it as a straight line because I didn't know, right? But we would want to draw this really like this at this point, since we know what this shape is. That would be better. And what would the angle here be? Well, 120 degrees is ideally what a trigonal planar structure has, but this now has the effect of a lone pair there. That kind of looks like a smiley face. But anyway, it's going to be less than 120 degrees because of the effect of that lone pair. Remember, that lone pair on the central atom there is going to take up more space, and it's going to push and contract that angle down less than its ideal 120 degrees. We don't know exactly what it'll be, but it'll be less than its ideal 120 degrees. All right, guys, we'll see you in the next video.